Next, we have Satchit talking about stability is stable connections between replicability, privacy, and adaptive generalization. So thank you, Satchit.
So hi, everyone. Today, I'm going to be talking about recent work on connections between various algorithmic stability notions, which is joint work with the listed co-authors. The structure of this talk will be as follows. First, I'll talk about the context and motivation of our work. Next, I'll explain our key contributions. I'll define an important quantity that we use in our results, and then formally describe our results. So to give you some context, we're interested in the replication crisis in empirical science and machine learning, where many prominent empirical studies have been shown to be bogus. When the same study was carried out with different data, the same results were not obtained. And the headlines shown describe some instances of this over the last 10 years. And these studies violated a fundamental principle of science, which is the principle of replicability. And replicability is the principle that the same study, when carried out on new data, should produce the same results. And the primary purpose of ensuring replicability is to avoid overfitting to the analyzed data. And the idea is that obtaining the same consequences on new data guarantees that this is unlikely. However, for complex tasks, it can be hard to define what counts as a successful replication. And with this motivation, Impagliazzo, Pitassi, and Sorrell last year formulated a precise quantitative definition of replicability as a stability property of algorithms. And the goal was that this property could certify that the output of an algorithm was not overfit to its data, and also that this property could be efficiently audited. And so they came up with a simple definition that can be applied to any statistical task involving IID samples. And the definition is as follows. A randomized algorithm is said to be row replicable if for all distributions D over the data domain, the inequality on the slides hold, and I'll unpack this inequality slowly. We're interested in algorithms that can have two sources of randomness from the data, and other random coins that may be used by the algorithm. And these are separated out into S and R on the slide. The principle of replicability asks that an algorithm not depend too much on the randomness that's inherent in the data. And so we ask that if we run the algorithm twice, keeping the same random coins fixed in both runs, but using two different randomly drawn data sets, then we get the same outcome with high probability. The parameter 1 minus rho indicates the probability with which we want the outcomes to be the same. And we want this to be close to 1, and hence we think of rho as ideally being close to 0, like a small constant like 0.01, for example. A work by Gazi, Kumar, and Manurangsi also formulates an essentially equivalent definition under a different name, and we rely heavily on techniques from their paper as well. So our work was broadly interested in general connections between differential privacy and replicability, and what new insights we could derive about both these notions from such connections. And there were a few reasons we suspected such a general connection. First, relatives of the replicability definition have been used to design state-of-the-art algorithms for some DP learning tasks. And additionally, the work defining replicability gave replicable algorithms for various distributional tasks that looked a lot like differentially private algorithms for the same tasks. So we suspected that there may be a more general connection at play. And now I'll tell you about our key contributions. First, we give tight statistical equivalences between replicability, differential privacy, and some other widely studied notions of stability. We look at computational separations between these stability notions, and we leverage these connections to solve problems related to all these stability notions, including giving new replicable algorithms, giving a new framework for differentially private algorithm design, and some other applications that I'll discuss later. Okay, so before telling you about our results, let me define perfect generalization, which will be important in our results. And this was formulated in work by Cummings, Liggett, Nassim, Roth, and Bu in 2016. And it asks that a randomized algorithm is epsilon delta perfectly generalizing if for all distributions D over the data domain with high probability over two data sets S and S prime drawn independently from the distribution, that the output distributions AFS and AFS prime are epsilon delta close. And epsilon delta closeness is in the same sense as in differential privacy. Okay. And since the algorithm's output distribution on two IID datasets needs to be close, the output cannot depend very much on the specific input sample that was received. So without going into detail, one motivation of this definition is that classifiers satisfying this notion cannot be post-processed in classifiers that don't generalize. And this can be important when we want to use classifiers for downstream tasks. It also provides a distinctive flavor of privacy that I won't go into just for time. And now I can tell you about our results. So they will involve the three stability notions that we've looked at, and will involve transforming an algorithm satisfying one of these stability notions to algorithm satisfying the other. And these transformations will preserve accuracy for a broad class of statistical tasks that I'm purposely sweeping under the rug, but it captures essentially any distributional problem involving IID samples, so hypothesis testing, distribution estimation, regression problems, confidence interval creation, clustering, so on. Okay, so a green arrow will be used to represent an efficient transformation in terms of time complexity. So our first main result is that you can transform an accurate, perfectly generalizing algorithm into an accurate replicable algorithm with a 1 over rho squared blow up in sample complexity. That is, if you start with an accurate, perfectly generalizing algorithm with n samples, our transformation gives an accurate replicable algorithm with n over rho squared samples. We also give a transformation in the opposite direction, converting an accurate rho replicable algorithm into an accurate, perfectly generalizing algorithm with a modest blow up in sample complexity. We show that approximate differentially private algorithms can be converted into perfectly generalizing algorithms with a quadratic blow up in sample complexity. And then finally, we show that a replicable algorithm can be converted into a differentially private algorithm with a modest blow up in sample complexity. And so the point is the connections that we draw show that you can convert from any notion of stability in this picture to any other notion by just following the arrows. And it turns out that this can be used for a number of applications concerning these notions. So one direct application is that this gives us new replicable algorithms, because this just comes from the fact that differential privacy can be converted to replicability with like a polynomial blow up in sample complexity. There's also a bunch of other applications, and for the rest of the talk, I want to focus on the ones related to differential privacy. So I'll describe the transformation from replicability to differential privacy that was developed over a sequence of works, and this gives a general framework that I think is useful in many differential privacy applications. So sort of the key benefit of the replicability definition that we will exploit is that replicable algorithms, when run with common randomness, have canonical fixed outputs that may depend on the randomness, but are sort of independent of the data set. And it turns out that this plays really well with the sample and aggregate framework. And this will become clearer when I describe the transformation next. Okay, so we want to convert replicability to differential privacy. How do we do this? First, we take the data and we divide it into k parts. Then we draw common randomness and run a replicable algorithm with this common randomness on each of these different subsamples, which gives us a number of outputs. And now we select a single output by simply applying differentially private heavy hitters. And this identifies a commonly occurring output that occurs more than 50% of the time. And the state-of-the-art private pack learning algorithms actually use a template that's very similar to this. So why does it work? Let's quickly describe the analysis. To analyze accuracy, so if we use an accurate replicable algorithm that guarantees a dominant OI that is also accurate, heavy hitters identify such a dominant OI as long as k is large enough. And so together we get accuracy. So what about privacy? So note that DP heavy hitters is robust to changing a single one of these OIs. And changing one data point in the input sample changes at most one of these OIs. And so this gives us differential privacy. And it turns out that this general approach of using heavy hitters plus replicability is more generally useful as well. And next, I will describe one such application concerning user level privacy. So I said that changing one data point changes at most one of these OIs. But you can also see that changing one entire data subsample, SI, also changes at most one OI, which is what will be useful for user level privacy. Okay, so what is user level privacy? In user level privacy, users have many data points, and we would like to maintain privacy with respect to an entire user's data. And this is in contrast to what we'll call item level privacy, where robustness is only with respect to changing a single entry in the data set or one point in a user's data. Okay, so the way this works is we modify the prior framework, and we simply think of each user's data as a subsample in and of itself. And then we can apply the same framework. So each user can apply a replicable algorithm to their subsample. We assume they share common randomness. And then they send their outputs to a central server that can just select one using heavy hitters. And this gives you user level privacy by the same analysis that we just discussed. Additionally, recall that our transformations gave a way to convert an item level differentially private algorithm into a replicable algorithm. And so combined with this, that gives us a way to convert an item level to a user level differentially private algorithm. And how does this work? Each user can use an item level DP algorithm in conjunction with our transformation from DP to replicability to design a replicable algorithm apply this to their subsample, get a set of outputs, and then just use the same framework. Send it to a central server, uses heavy hitters, everything works. So now let's take a step back and sort of assess. One advantage of this transformation is that it's very general and it needs very few users because you just need enough users to make heavy hitters work, which is often not very many. On the other hand, there's a big constraint, which is that you need a few users with lots of samples because you need that a lot of these OIs are accurate, which means you need users that are sample rich enough to solve the problem for themselves, which can be a pretty significant constraint. But a very nice recent work, which is I posted session 3, and it's called user level differential privacy with few examples per user. It shows that such generic transformations can also exist when users have much fewer samples. And it uses different techniques, but also relationships between different stability notions. So if you're interested, I'd encourage checking that out. Okay, so that's on user level privacy. I want to just sort of illustrate how useful this framework is by talking about one other application, which is on interconversions between privacy notions. And sort of the question is, can we generically convert from one differential privacy variant to another? So we have so many now, right? As an example, can we convert an accurate approximate DP algorithm sort of to an accurate truncated ZCDP algorithm, zero concentrated differential privacy? This is another notion of privacy in case you haven't heard of it. And it turns out that our framework gives you a way to do this. So again, you divide the data set into subsamples, and we have a 1, delta differentially private algorithm that we want to convert to a truncated ZCDP algorithm. You can use the conversion from DP to replicability to get a replicable algorithm, apply that in a bunch of subsamples to get a bunch of outputs. But now you just use a truncated ZCDP heavy hitters algorithm instead of an epsilon delta DP algorithm. And again, by the same analysis, this overall algorithm now satisfies truncated ZCDP. But there's also nothing special about truncated ZCDP. You could use your heavy hitter satisfying your favorite privacy notion at the end, and then the overall algorithm would satisfy that privacy notion. You also don't need to use approximate DP here. You could replace approximate DP in the input with many other notions of privacy, and this would work as well. So you can also use this for privacy amplification. So for example, in approximate differential privacy, we didn't previously know how to asymptotically amplify the delta parameter as a function of the sample size. And so what you can do is, let's say you have a 1, delta DP algorithm where delta is like, let's say, polynomially small in the number of samples n. You can convert it into something that's like almost inverse exponentially small by just instantiating DP heavy hitters with sort of your target delta parameter. And so this gives you a way to generally amplify privacy parameters as well. I do want to mention that there are obviously constraints that come with this type of generality. For one, you see a quadratic blow up in sample complexity, which comes from this DP to replicability conversion. And if you try to directly design algorithms satisfying privacy notions, you would not see this quadratic blow up. And also this overall transformation is computationally inefficient, which sucks. Okay, so I'll conclude there, but I just want to say that there are many other applications of the paper that I didn't have time to touch upon. And we also have statistical and computational separations in the paper that I find very cool, but I'm happy to discuss this offline. So catch me in the breaks or at post the session 3. Thank you.
Do you have any questions for Satchit? I have a question. So we just heard a talk about privacy and robustness. Do you think that the picture you had before of a triangle is a square?
Well, it is a square because there are like other stability notions that fit into it. You can probably make it a pentagon or an octagon even. I do not know if robustness can be a vertex on that polygon. Mm-hmm. Yes. I didn't talk about this, but this basically. Oh, I'm so sorry. They basically pointed out that you can come up with general transformations by just tossing out your data and doing nothing interesting, but this doesn't preserve accuracy, and I didn't talk much about accuracy. And the reason I didn't talk much about our accuracy is because for a very broad notion of accuracy that I didn't go into for technical reasons, our transformations essentially preserve accuracy. Yeah. again, so the formal definitions in the paper, and I'm happy to discuss them more often.
Fantastic. Perfect.